Well, hello everyone. Thanks for being here for my talk. So yes, I'm David Fuenmayor and I work at the AI Systems Engineering Department of the University of Bamberg. So who am I? I'm a previous Java/.NET developer, so enterprise applications. Java folks out there understand what that means, or maybe they just forgot and don't want to remember. So over the years, I sort of converted myself into what people might call an academic, in a sense. And I work in a university, as most academics. And we teach logic. I will elaborate into that right now. So logic, but with the idea of automating logical reasoning. And we have had this course since 2023, and this is a summer course. So we always teach this course when it's nice weather outside, so we get only the die-hard students attending. And yes, I'm an Elixir enthusiast, also because of this course, in a sense. We had to make a choice of which programming language we wanted to use to teach the students how to do this automated reasoning thing. And the usual suspects tend to be functional programming languages, so, you know, ML, right? By the way, ML is a programming language. But well, OCaml, most well-known, or Haskell, right? And well, we took Elixir. We think it's the most approachable functional programming language out there, and we loved it, and I loved it. And so a little more about our group. So as I said, it's AI Systems Engineering, and it's led by Professor Christoph Benzmüller. He deserves an honorable mention because he was the person who showed me Elixir and showed me that this existed. And so he brought me into this. And we are specialists in this area of automated reasoning, in particularly Professor Benzmüller, who was my PhD supervisor. And well, what is this automated reasoning thing? So it sounds like it's some kind of symbolic AI, good old-fashioned AI thing. Yes, it is, but it's even older than that, right? And we can think back of Leibniz. He has this famous Calculemus manifesto. So the story is more or less that he was sort of annoyed with these philosophers arguing, talking past each other the whole time. So he wanted to build a machine where he could encode like arguments, say philosophical arguments, but that can be a mathematical proof. And this machine will sort of say yes or not if your argument is logically sound or not. And for this, he conceived of a universal language, which is, he referred to it as a characteristica universalis. These days, we will call it logic. Well, there are many different logics. I will come to that later. But it's fair to say that, nowadays, intellectual heirs of Leibniz, in a sense, are the people who work in this area of automated theorem proving, automated reasoning. And SAT, SMT solvers, many or few, well, some of you have heard about SMT solvers or model checkers, maybe constraint solvers. All these things sort of belong to this automated reasoning area. And also proof assistants. So proof assistants, think of them like IDEs for developing proofs or mathematical theories. And there are many of them. Those three are like the most mainstream ones. Isabelle, Lean, and Coq, which I recently found out the Coq rebranded themselves as Rock for some reason. Anyways, used to be called Coq. And well, automated reasoning in AI. So how does it make, what is the relationship, right? So here is more or less the way we would approach a problem in automated reasoning. So we have an inference, right? I think this is, well, we have an inference here, right? So we say we have some assumptions, right? If we are doing planning or think of a computer judge, right? Say the assumptions is the judge has to sort of decide whether to send some guy to prison or not. So there are like the assumptions, what happened that day, what did the guy do, and the conclusion is like the verdict, right? Guilty or not. But this inference, right? It's an argument. If we look at it, And it's always taken with respect to the background theory, right? So that would be the legislation. And this background theory, in this approach, automated reasoning, it's encoded as a set of formulas in some logical language. And same here, right? The assumptions and the conclusion, they can be modeled as some kind of mathematical structure, think of a graph, or as a set of formulas. So if you model them as a mathematical structure, as a graph structure, you have a model checking problem. If you model them as formulas, right, so a set of formulas or assumptions encoded as formulas, and the conclusion or the theorem, if you're doing math, then well, all these things are formulas, and we can check whether these formulas together derive a contradiction. If they don't derive a contradiction, we call them, we say that they're together satisfiable, right? So it's allowable to draw this conclusion under these assumptions. And this problem is also being called a model generation, because to show that something is satisfiable, you need to sort of produce a mathematical structure that shows how the world would look like if all these things hold, right? Because if they're contradictory, you cannot come up with such a model. But more this later. If you want to do proof, so basically proof is an instance of unsatisfiability. So basically means it's impossible to have both the set of assumptions, the background theory, and the negation of the conclusion together as a consistent set. And normally you show this by making a derivation, by deriving the conclusion from the assumptions modulo the background theory. And that's what automated deduction, automated theorem proving does. But well, I said in a logical language, well, which logic? Logicians keep coming up with logics every day, and there's a couple since we started talking here more, so which one? So that's where the research of our group is like focused. So the idea is that we try to translate problems in different logical formalisms, like this temporal logic, modal logics, and so on, into higher order logic, right? So the idea is to being able to use domain-specific knowledge, right, of your application domain to carry out derivations or model generation via translation, right? So this object logic, for instance, it will be temporal logic, for instance. And domain, your application domain might be program verification. So program verification on temporal logics, and the problem gets translated into higher order logic, and we apply these theorem-proving algorithms for higher order logic in order to solve this problem. And well, here is a reference to a paper if you want to know more. I think I still have some time, so I will discuss. Well, I've been talking about this higher order logic thing. You maybe remember from university or not, but well, that is first order logic, which is like the mainstream thing. And in first order logic, you sort of quantify, I mean, you can say things like for all x, f of x satisfies predicate p. So for all x, the father of x is patient or proud, or so that's first order logic. That's all you can do. Or you can say, okay, there exists an x such that. But in higher order logic, we have all these other additional expressivity. So we can quantify over functions in this case. So we can say for all functions f, p holds of f of a. We can quantify over predicates. So we can say for all predicates p, p holds of f of a. And well, we have lambda abstraction anonymous functions also, and we can make definitions. And we have types, of course. So it's actually, higher order logic is another name of referring to the simply typed lambda calculus plus logical constants. So simple type theory, some people call it. So yes, these are arrow types. And so well, so theorem proving in higher order logic is different than in first order logic, basically because you have more choices. So the language is more expressive. So when you're in your search, you have more branching points and more options. You have infinitely branching search spaces. So, but it's not all bad, right? It's more complex, but it's more rewarding because you can get shorter proofs and more insightful proofs, in a sense. So, yes, theoreticians like to call this undecidable, but well, we call it interesting because it's a problem that combines also AI, in a sense. You need to come up with heuristics, you need to integrate knowledge of the application domain to do this proving. So it's interesting. And yes, proofs in whole are arguably short and elegant, and arguably more intuitive. And well, I want to go more into this. So yeah, the slides, I actually stole them from Christoph, the head of my lab. And we have with him a paper out there where we sort of elaborate on this point. So yes, you can look at it. For now, well, last but not least, there is this quote like that higher-order logic is set theory in sheep's clothes. Quine was a famous logician. And there is an interesting theoretical connection to Elixir set-theoretic types here to make, and I'm happy to talk about this afterwards. So well, let's move to our course, right? We don't have much time. So it's a summer course, as I said. We have hands-on and tutorial sessions. In Elixir, students learn how to write these theorem provers in Elixir and using Livebook, right? So for some kind of interactive group programming sessions. So think of it as like the orgiastic version of pair programming. So because we can do these things in Livebook, so it's great. And well, it's a master course, so it's not mandatory. That means we get students from other universities who didn't have our logic courses, our bachelor courses. Oh, sorry, talking too fast. So this means we have a challenge here. So it's the first logic course for many of them. And what do they do in their first ever logic course? Well, since it's a master course, it's an optional one, we make our own rules. So we decide what to teach them as a first approach to logic. So we teach them simply type lambda calculus in higher order logic. And they do remarkably well. And some people, many of them have some experience with lambda calculus, even if only intuitively. And if some of them have done some JavaScript, so they're familiarized with callback hell and these things. So they have an intuition for higher order functions, and they grasp the theory behind these things quite well and quickly. So in the last 5 minutes, so I will now move to some demos. So don't worry, there will be some code. The demos I'm going to show are in this GitHub repository. So those are basically Livebook examples with the demos I'm going to show. The idea is that we will be moving the course material like slowly towards this repo. So these are some of the techniques we teach the students, and they will get the corresponding Livebook in this repository. So now as for the demo, so let's quickly show you how this looks like in practice. So there is this method of tableaus, which basically means it's a method based in what people call the sequent calculi. It's like, and the sequent calculi, okay, this is how logicians dream, right? People in proof theory, they think in this language. It's called the sequent calculus, but bear with me, it's not as bad as it looks like. So basically it means like, if you want to prove something that has this form, your conclusion is an AND, right? This means you need to branch and check whether A follows from gamma and B follows from gamma, right? This is a branching rule. And you have rules that are not branching. So if your assumption is an AND, you can add both assumptions to your list of assumptions. So it's a non-branching rule. So this looks like, so you might think, okay, how do we teach students to encode these rules in Elixir? Well, pattern matching. And it's pattern matching all the way down to truth, so to say. So here, our provers are just pattern matching, pattern matching, pattern matching. The rule I just showed, for instance, this one, if the assumption has an AND form, then we call recursively the Tableau procedure and pass the two to the list, right? So it's just pattern matching all the way down. And for the branching rules, right, we can invoke this strategy. Basically, we can choose how to branch, right? Because Elixir allows us to do this higher order functions, right? So a strategy pattern, if you wish. So we can branch in different ways. We can invoke processes recursively. We can branch using different processes. So this is good because, as I said before, theorem proving higher order logic is highly branching. So we have discovered, like sort of anecdotically, that Elixir actually improves a lot the performance of its provers because of this. And another demo, well, honorable mention, 2 of our students remained in the Elixir world, and they're doing their master projects in Elixir, right? And one of them is implementing a full higher order logic prover. The other one is doing a framework for hybrid AI in Elixir. And so you can visit their repositories. This work in progress, right? They're not finished yet as the time of this talk, of this recording, but they have interesting things. And in particular, this here, the so-called unification procedure is already working. So, well, how does unification look like in Elixir? This is a well-known algorithm that is like a general purpose algorithm for many things, including type inference and many others. And it's pattern matching all the way down. Pattern matching, this is an application of a function. This is, it's just pattern matching. It's incredible. And I'm very happy with Elixir. I can basically type these sequence things, and it's just pattern matching. So they translate almost one-to-one isomorphically to code. So to finish, since I don't have quite much time, but let me do some finer proselytism here. I recently programmed wrote this library for connecting to the Isabelle proof assistant to do some experiments, right? So, well, how does it look like? Just very quickly, you connect to the Isabelle proof assistant. You write a problem in the Isabelle language, so it looks like this without syntactic sugar. And you basically want to verify a theorem that says that if a relation is reflexive and Euclidean, then it's also transitive. And there is this conjecture that says that if a relation is reflexive and transitive, then it is Euclidean. The first one holds, the second one doesn't. And we send this to the Isabelle server using the library, and we get back some string. It looks like this, basically. So Isabelle calls a lot of automated theorem provers in the background. They verify the first claim. So several of these theorem provers come back with affirmation that say, yes, this is a proof. And it comes back with a counter model, right? So this is a binary relation. It's a counter example to the claim that reflexivity and transitivity imply Euclideanness. We can parse this thing, right? Using Elixir, and well, we can build a map. So we have here a map. So it's basically, well, we can read this as a graph, right? It's a relation that relates A to itself, to B and to C. Well, relates A to everybody, B to itself, C to B, and so on. And well, we can do some downstream work on this. We can create a directed graph using Erlang's standard library, and we can use standards, Erlang standard library to do some interesting things like computing the topological sorting of this graph, right? So it's a graph traversal in which each node is visited only after its dependencies are visited. So we can do many downstream interesting things by interfacing with Isabel model generation. So you can call this generative AI if you wish, but without hallucinations. So yeah, that's I think that's all I have for today. That's the corresponding slide to the project I just mentioned. And so this is the overall idea, the things we want to do for the future. Okay, and now, thanks for your attention.